Good morning. How is everyone? I hope everyone's okay. It's a nice, relaxing Saturday. Thank you very much for joining. Really appreciate it. I've actually sent out an invitation. To a lot more people because it's actually a paper 6. I'll just adjust the levels. So today we're going to be going through the alternative to practical, the paper 6. Paper 6 is actually the next area that I would recommend that you try and get your focus on now, because previously what we did was we broke the ceiling. We got to the 44. So you're all C graders. Congratulations. Now, the next thing that we're going to be doing is we're going to be focusing on paper 6, because when you look at questions like this, right? When you look at questions, this is from 2019, and please, if you have the mark scheme, don't look at the mark scheme, okay? Because I'm just literally going to be taking you through it, and there's stuff on the mark scheme. I've had a look at the mark scheme, and you need to have someone to actually see the whole paper for what it is, right? And what the mark scheme won't do is it won't tell you how to strategize against questions like this. This is actually, I'm not going to go into this question just yet, but this is actually a horrible question. It's actually a horrible question. I actually don't like this question. Okay, there's very few questions that I don't like. But this is all right, I'm going to go out on a limb, all right? I'm going to go out on a limb, all right? Nothing too controversial. I actually think, my own personal opinion, just without any extra knowledge whatsoever, this is actually a badly designed question. I said it. It's a badly designed question. Because I look at this, right, and I think, hi, chill beans. This is actually a really badly designed question, okay? And the reason why I think this is a badly designed question is because if I was a year 11 thinking that everything is on the line for an iGCSE and I've done all of this prep and all of it is kind of like culminating in me sitting in this exam hall and I read this, I would freak out. And even just looking at this question, I started looking at this question just before I came over here, right? And this question isn't hard, okay? This question, right from the very top, this question is not a hard question. Look, let me reassure you, okay? This is not a hard question, okay? But what they did in 2009 was an absolute travesty. They put this many words in it. And you look at stuff like this, right? You look at that, and you just think, that just messes about with what we called cognitive load, okay? So this puts a huge amount of cognitive load. It strains your mind. And in an exam situation, that's awful. I need to sip my orange juice just to calm myself down a little bit about that. So I am on your side, okay? I am on your side. And I have looked at this question and I was like, you need some reassurance. Right, okay. Because what I'd like you to do is this, right? And put it in the chat, right? Put it in the chat. If you've ever freaked out looking at a paper 6, right? You must have had a look at a couple of papers. If you haven't looked at paper 6, right? That means you're freaked out anyway, so you can tell me, right? But if you have actually looked at a paper 6 question, right? A paper 6 question, and you look at this and you freak out, I want you to put it in the chat, and I'll read it as I make a start on this, okay? Now, okay, right, so promise, you're not looking at any mark scheme, okay? Promise, right? Okay, so I'm going to try something different today as well. I'm going to be using text boxes just to make it a little bit clearer. And of course, this was not forced by the fact that I may. I can't fib to you. I may have just left my stylus at school. I know. All right, okay. Let's have a look at this question. Right now, what I'll also do is I will link the question, because I remember this from last week. I will link the question. You got to promise me, don't look at the mark scheme, okay? Don't look at the mark scheme, all right? All right, trust me, please. Okay, trust me. Don't look at the mark scheme. Please. I send you this link. You know, it's on the Cambridge website, right? I will send it to you. Okay, so I'm going to put that in the chat. So I want you to be loading out. All right, but we're not looking at the mark scheme, okay? All right, don't look at the mark scheme. All right, there it is in the chat. Okay. Okay, there it is. It's in the chat. All right, so just please don't look at the mark scheme. Please, don't. Like, I will send you, listen, right? I will send you the mark scheme at the end, okay? And I'm going to be referring constantly to the mark scheme throughout, okay? But don't look at the mark scheme, please. Don't. Okay, all right. Anyway, so we start off. Let's make a start. Are we all ready? Juice box. Honestly, we have discovered this, right? Here we go. So this is part of a journey that we have taken. Okay, this is part of a journey that we've taken because wherever I am in the world, I've got to sort my juice out. I've got to sort my juice. So I have to sort my juice, right? And one of the things that challenged me in the UAE was that to actually figure out that you've actually got a pure juice and not some kind of nectar, which is sugar, basically. Or like, okay, so I went to 100%, but then even when it says 100%, you gotta be careful. This is actually a juice blend, okay? And I can totally understand because carting around liquid in the UAE isn't fun at all, and it gets very, very expensive, okay, even though the petrol prices are depleted. So this is like orange juice, apple and grape juice, and it's actually not right. It's actually really nice. I don't mind having a blend of juice if it comes from a different fruit. Don't click the masking. Don't click the masking. All right. Okay, enough about juice. So juice, yeah. Juice. A juice is always good. Have a juice. I would recommend if you ever like starting to get a little bit stressed about chem, enjoy a little experiment. Okay, right. 471. By the time I finish your number, the latency will kick in. Now, when you say the one on the left is a flask, okay, thank you very much for your first contribution. Okay, first contribution, we like that. Okay, but I'm gonna come out straight with this one, right? So you get a couple of emotes for first contribution. Well done. All right, but I'm gonna come out with this one. Flask, to me, is the most unnatural term that a student will come out with. Okay? Yeah, it will. And I know. Yeah. Now look, the thing is, it says flask 1, right? It says flask 1 underneath here, okay? So it says flask 1, right? And then you call it a flask. So I don't understand. Yeah. So if you actually says, right, it says flask 1, and then it says use the diagram to, it says complete the box name or apparatus. Are you just going to call it flask again? It does not tell. It does not say. It tastes sweet. It tastes sweet. Yeah. So no, no. We don't call it flask 1. All right. So it says complete the box to name the apparatus. Okay. Now we actually did have someone suggest different. Okay. Now this is how. This is how demented. How demented. And silly. The iGCSE is, right? This has to be the easiest mark. The easiest mark. Not because, and 471, you are correct. That is a conical flask, which is, I believe, sometimes known in the business as an Erlenmeyer flask as well. And don't worry about Erlenmeyer, because I did not even know what an Erlenmeyer flask was before I actually went to uni, because I didn't go to Allen English speaking schools, and I know that, that's about achieving excellence. I went to a school that just short of it. But still, I didn't even know what Erlenmeyer flask. Not until I went into university, right? And I walked into the lab, I was like, and they said, "Oh yeah, just go get an Erlenmeyer flask." I was like, "What?" And they said, "Go get another." I was like, "What? You mean a conical flask?" Yeah. I was like, "Why just call a conical flask conical flask?" And then they taught me. They said, look. This is called an Erlenmeyer flask. It's named after the person who actually it's named after a very, very, very important chemist. And I was like, okay. Now, another name for it is called a titration flask. And that's actually really nice. Because you do use it in titration. It's got a flat bottom, okay? It's got a conical body, like an ice cream cone. So I was like, oh, right, okay, ice cream cone. So when you hold an Erlenmeyer flask, you hold it upside down, don't put any liquid in it, right? And you hold it, it looks like an ice cream cone. And that's the way that I always taught it. Conical flask, all right? Apparently created in 1860 after the German chemist Emil Erlenmeyer, okay? All right, it's usually got a beaded lip, and you can put a little stopper on it. So it's actually really, really good, all right? So, me teaching you, I'd put conical flask, okay? I'd put conical flask. Now, the mark scheme is so silly that they'll actually give the mark for you just saying this. I don't get that. It's like, this is flask 1, name it. Flask. You get a mark. I was like, what? I was like literally, what? So in the mark scheme, don't look at the mark scheme. In the mark scheme, they actually don't fret about what name you put at the start. So you could put Erlenmeyer, you could put conical, you could put titration, you could put what? They're just accepting flask 1 mark. It's easiest mark in the paper. I think I can't believe that this went through. Like, because exams don't just get made up like I make exams up over the weekend for a class. They go through a series of different stages, right? and lots of meetings, lots of very, very experienced examiners and examineresses, right? Yeah, silliest mark, silly mark. Okay, right. The second one, what's the second one? The second one, the one on the right-hand side. What do you think that is? What do you think that is? Okay, so it seems to be a container that can collect gas. Seems to be a container that can collect a gas. It's a container that can. Now, I know someone's going to say syringe. Right? It's not a syringe. A gas tube. A gas tube. I've never ever heard of a gas tube. I've never heard of a gas tube. I wonder whether it exists. Is this something that you have been taught before? Gas tube. Okay, let me just see what's now you get gas tubes for pistols and rifles. No, that's not right. Okay, what's this? Gas system parts at Brownells. A gas tube is actually part of a gun. Sorry, it's not a gas tube. And I'm not gonna quote that. Okay, it's not a gas tube. It's not a gas tube. A gas jar. Yes, it is a gas jar. Okay, right. I just forgotten. Okay, so gas jar. Okay, right. You've heard of a jam jar, right? See, gas tube stressed me out. That's my tell. That's my tell. So that stresses me out less. Bits stress me out less. Okay, right. So gas jar. It is a gas jar. It is a gas jar. So right. Okay. Let's commit. All right. So this is. We're gonna go with Conical Flask. Look at that font. That font kicks. Look at that. Gas jar. There we go. Can you read that? Yeah. Look at that. All right. Is that all right? Yeah. Are you entertained? Yeah. Is that good? All right. That's good. Okay. So we've done that one. Use the diagram to identify two mistakes the student made. Right. At this stage, you know that you have to go back to the original question and read it. Okay. Because like you went straight into the question, started calling that gas tube and that flask. Right. The diagram shows that the apparatus a student used to prepare a dry sample of chlorine gas. Okay, chlorine is more dense than air. What does more dense than air mean? Will it rise or will it fall? Okay, more dense than air. Okay, rise or fall. So more dense than air. Rise or fall. Rise or fall. More dense than air. Does it rise or fall? All right, okay. We're not too sure about density. Okay, density in physics is defined as mass over volume. Okay, so high density means large mass in a particular volume, so it'll sink. Okay, all right. We're gonna have to look at the wording of this. Okay, so we found something That's a weakness, okay? Now, the weakness, let me see if I can get a really good, okay, right, here we, okay, right, so if I do this, this may help, okay? All right, so, yeah, I know it's key stage 3, it's year 7 and 8, all right? Okay, just rest assured, we found a weakness, okay? So, physical changes. The density is mass divided by volume, okay? It's something that you use to close the conical, right, okay, first things first, you're collecting a gas, all right? Going back to here, you're collecting a gas. The first thing that you need to ask yourself, when you have a question, now I know that I've not taken you through stuff like this, okay? So here's my tip. Whenever you have use the diagram to identify 2 mistakes. Whenever you have a question, ask yourself, will the experiment work? Okay. That's the strategy. Okay. That's the strategy that I'm using. Okay. Will the experiment work? All right. Okay. Will the experiment work? Okay. Right. Let's go back to density. Okay. You can't get around this. Okay? You're going to have to learn density. Okay. The more dense a substance is, the heavier it feels for this size. All right. The more dense a substance is, the heavier it feels for its size. Okay. All right. So that's the website. Okay. All right. All right. So you can go on there. Open that up after the. Open it up after. Okay. And see if there's another, like one with a picture or something like that. Okay, let's have that. Oh yeah. You know what? You did this. You did this in year 7, like ish. So you did something like a density jar where you had like honey at the bottom, and then you had like water, and then you had like, you know, oil and stuff like that, and it went in different layers. And then you dropped a nail in them or something like that. You dropped a nail, you dropped a coin, you dropped well, I do this, and I would expect people coming in like from primary school to be doing this kind of activity. It's like one of those fun activities that you get, like, and that really gets us thinking about it. So the blue liquid in there, the blue liquid is denser than the yellow liquid, okay? And the way that I see gases as well, because gases are like a fluid too. They're fluid, right? So if you have like a dense gas, right, it would, and the gas was denser than air, it would sink, okay? It would sink. So that means it would be like near the floor, or near the tabletop, yeah, or wherever your lab is, right? So do you understand now what density is, right? You don't have to work out what density is, okay? You don't have to work out what density is in chemistry, but you do need to be able to say, like what, you need to be able to identify that, guess, right? Okay, right, anyway. So that's the reason why the question ends with that second sentence. Okay, the question ends with that second sentence. So look at the gas jar. All right, look at the gas jar. Yeah. Chlorine is more dense than air. Look how it's being collected. Look how that gas is being collected. So ask yourself, will the experiment work? Yeah, will the experiment work? Chlorine is more dense than air. Will the experiment work? So what will a very dense gas do? In air, it will sink. Will the experiment work? So will the experiment work? No one's biting. No. Why? What will happen? What will happen? So you make your chlorine gas, right? Lovely gas that comes out here. Yeah. All right. Lovely gas. So your the chlorine gas comes in here. What's going to happen? Because the second conical flask should be clear. Right, forget about the second conical. No one cares about the second conical flask right now. No one cares. The experiment, yeah. Why? What's happening about the? All right, let's say, for example, let's say some chlorine gas gets through here. No one cares about that. The clue. What we need to do is we need to identify. We need to identify from the question itself. Yeah. From the question itself, because you don't. This requires zero thinking. This requires zero thinking. They require zero thinking because they're actually giving you the mark. The one that you're on about, the one that I'm avoiding, does require thinking. Yeah. That will be point 2. That will be point 2. But point 1. I'm going for point 1 right now because I know that that's tricky to think. And the reason why it's tricky to think is because you're showing a lack of confidence with density, which is how I'm putting you outside your comfort zone. Okay, so let's say, for example, you do have chlorine, right? So the question I'm asking is, will the experiment work? Okay, it won't work. Obviously, that's why I keep going on about it. Let's say, for example, the chlorine gathers up here. All right. Yeah. So what will happen? What will happen? There's your chlorine. Look at that beautiful chlorine bubbles just forming there. It's not actually bubbles. It just like comes out as an ordinary gas. So why? Why will it not work? Okay. Prepare a dry sample of chlorine gas. Chlorine is more dense than air. Chlorine is more dense than air. What will happen? More dense than air. Okay, what was in the gas jar before? Air. Okay. All right. Okay, there's air everywhere. There's air everywhere around here. Okay. There's air everywhere. Everywhere. Yeah. There's air everywhere. Everywhere around here. All right. Everywhere. Everywhere. Okay. What is that chlorine gas going to do? Come on, you can do it. Okay. Is it more dense than air or less dense than air? It's more dense than air. Okay. What's the chlorine going to do? Okay, right. So, you need another clue. Okay. Do you need another clue? Do you want another clue? Do you want another clue? Let me know. Oh, no. We're not talking about sulfuric acid. Don't complicate it. We're not talking about anything like that. All right. What is the chlorine gas going to do in that gas jar? If it's in the gas jar, what's it going to do? It is more dense than air. Do you want another clue? I can give you clues. You know, I want to get this one nailed. Yeah. What is chlorine gas going to do? More dense than air. What does more dense than air means? If I have a gas in my hand and it's more dense than the air that's surrounding it, okay, all right, and if it's in a balloon. All right. If it's contained in the balloon, and let's assume that the balloon is extremely light, it's virtual zero mass, like a bubble. Okay. If it's in a bubble, all right, and I'm able to hold it, and I release it, and the bubble is there, and it's more dense than air. What is the bubble going to do? Okay, its mass in that volume is greater than air's would be. Okay, so mass divided by volume. So if you have like two bubbles, one is just air, ordinary air, and the other one is like a gas that's more dense than air, then you would, and they're both the same size, then you would actually have a greater mass in the one that has the greatest density, assuming that the volume is the same. That's what physics is telling you. Do you want another clue? I can give you another clue. I can give you another clue. All right, I'll give you another clue. Okay, right. This is not as difficult as people are maybe thinking. Okay, because right, here we go. All right, here's another clue. Okay, all right, let me just drag it across. Okay, here we go. There we go. This is a big clue, by the way. Okay. This is another clue. Okay. Right. So my question is this, right? How do hot air balloons work? How do hot air balloons work? Okay, how do hot air balloons work? Okay, just type it in the chat so I can respond. Like, don't worry about the latency. How do hot air balloons work? Yeah, hot air balloons, right? Well, what do you do? What do you do to a hot air balloon? Yeah? What happens below here? You guys know about hot air balloons, right? Just in case no one knows about hot air balloons. How do hot air balloons work? Fill it with heat. You don't fill it with heat. What do you do? What do you do? You don't fill it with heat. Heat doesn't, like, what? Heat's not a substance. All right? Like, what are they doing? Like, literally, it's in the name, hot air balloon. We took a hot air balloon. Hot air. I'm having fun here, by the way. Oh my gosh! Are you serious? Helium? What? You need to get on a hot air balloon. Do you know that? Helium? No, it's not helium. Hot air. Okay, right. I need to explain to you what a hot air balloon is. Right. Okay. Look. Let's. Okay. Okay. Right. So let's have a look. Helium. My goodness me. Right. Let's have a look. What are they having after breakfast? Right. Hey, wait. They have a camel ride. Yeah. All right. And then they do all of that. Right. Okay. Here we go. Where is it? There it is. Okay. Right. Let's get to the. There was a really good bit. There it is. Right. All right. This bit. Look. Right. This bit. Okay. Okay. Right. What's in? All right. There's some tanks down here. Right. What's in those tanks? Yeah. What's in those tanks? It's a flammable gas. There's quite a lot of it in the Middle East. It's a hydrocarbon. And it's not helium. What is it? What's in there? Methane. Thank you. Methane. Good. So, good. Defo methane, right? So, the methane sets alight, right? Okay, because you put a light to it, right? It's an exothermic reaction, yeah? It releases a lot of heat. Heat is not something you fill up something with, right? All right, otherwise, heat is not a substance. What does that heat up? What does it warm up? Okay, what does it warm up? What does it warm up? What does it warm up? Oxygen. No, it's not oxygen. No, it's not oxygen. It's not called a hot oxygen balloon. What does it warm up? It's a hot air balloon. What does it warm up? Air. Thank you. Yes. Right. Are we good? Are we good with air? Good. Right, okay, all right. Oh, you guys make me laugh. Right, I just needed to gather my thoughts. Right, okay, so I'm going to ask you this question. I hope you can answer this. Can you describe to me how the particles in a gas like air move? Randomly, thank you. Good. And how would you describe the distance between gas particles, a gas like air, which is a mixture of gases, but to be a little more accurate, how do you describe the distance? What makes it different to a solid, or makes it different to a liquid? The distance between particles of air. Okay. How would you describe that? Okay, because this helps with the next question I'm going to ask. Large. Okay, it's a large distance, right? Okay. So, when you heat air, what happens to the speed of the air particles, and what happens to the average distance between the air particles? Okay, so when you heat air, what happens to the speed of the air particles, and what happens to the average distance between the air particles? Speed increases, correct. What happens to the average distance between the air particles? Distance No, the distance does not decrease. If the distance decreased, if you keep heating it, it would turn back to a liquid. The liquid particles are virtually touching. And if you heated it even further, it would solidify. So the distance can't decrease. All right? Okay. So distance cannot decrease. Else it'd solidify. Okay? All right? The distance increases. Yes. It has to. Has to. Yes. Increases. Okay, right. So now we're going to assume that the balloon is a fixed volume. All right? Takes up a fixed space. Now you'll notice that at the top of an air balloon, you actually have a little hole, and it allows for this. Okay, and obviously you've got a hole at the bottom. All right, so it allows for what we call expansion of air. All right, we know that if you have a methane like fire at this very beginning, it heats the air. Okay, and initially a balloon expands. Right, the balloon's expanding because the average distance between the air particles that are inside that balloon, including the products, carbon dioxide and any steam that comes out from the water, it's expanding. The distance is increasing all the time. That's how hot air balloons get inflated. Okay, all right. So this is quite an important point. Okay. So now I'm going to go back to the paper. All right. Because if you have let's have a look. If I just do a circle here, all right, and then a circle here. Now, both of these would be assume that they're both the same hot air balloon, all right. Assume that they are the same volume. Okay. Now, from what you've just said, the air particles inside the colder one have a smaller distance between them. Okay. Because their average speed is lower. Okay. All right, I think I've done sufficient. No, I don't want to do that now. I want to do that here instead. Otherwise, you see it as a lattice. Now, when you heat the balloon, gas particles escape because you're speeding them up, and the gas particles that are left behind are moving faster. They're whizzing around faster. Okay. So you can imagine that they're rebounding each off each other, but they're all right. But these ones, they're moving slower. Okay. So the most important point to figure out is how many gas particles are in the warmer one compared to the colder one, and the answer is obviously less. Okay. There's less air particles in the warmer one. Okay? Now, this is where we make the leap to the mark. Okay? So, if there are less air particles in the warm one, if it was possible to weigh both inflated balloons, the warm and the cold one, which weighs more? Which weighs more? It's an obvious question, because each particle has, let's say for example, each particle has the same mass. Okay, it's like average. No, we're averaging out. We know it's a mixture, but let's just say gas particles, right? Okay, which one would weigh more? The one that would weigh more would be the one that contains more. Okay, so which one weighs more? Which one weighs more? Which one would weigh more? The blue one or the red one? The cold one or the hot one? Which one weighs more? Which one weighs more? The one with more or the one with less? Which has a greater weight? Come on, take a guess. Which one? Right, everyone take a guess. Okay? Everyone take a guess. We'll see if as a collective you're correct or not. Everyone take a guess. So which balloon would weigh more? Would it be the cold balloon? Or would it be the balloon with the heated air that has had some of the air escape? So it contains less air particles. The cold one is heavier. Thank you, Divine Shoe. Thank you, Divine Shoe. Okay. Do you all agree? Do you all agree? Chill Beans, what do you think? 471, what do you think? Q Hosel, what do you think? Yes. Okay. Right. Good. I'm so glad that you've said that. I'm so glad that you've said that. Because this is basically how hot air balloons work. Now, if you imagine that you have heated your balloon, and we don't have like balloons for we actually have hot air. So if you imagine the rest of this around the hot air balloon, is made of cold air, what's going to happen to your hot air balloon? Okay, what's going to happen? Is it going to fall or is it going to rise? Okay, is it going to fall or is it going to rise? Okay, is it going to fall or is it going to rise? Do hot air balloons fall Or do they rise? Hot air balloons fall, do they? When you put... Let's find out, shall we? All right, there you are. You're heating the air. Oh, look, there's one that's inflated. It's beginning to rise. Let's heat the air. Let's make the particles move even faster, right? So there's less of them in there because the average distance is greater between them. Okay? Look. They're rising. The hot air balloons have taken off. Yes? Chillbeans, they were fallen. They were resting on the floor before you heated them. You actually had to heat the air inside. Science is not wrong on this one. Science is right on this one. Science is right on this one. Right. Okay. Science is right. So, let's come back to this. Okay. Now, here we have, like, remember what I said, density equals mass over volume. Okay? Density equals mass over volume. So over here, this has a large mass in the volume. Okay? Okay? In the colder one, all right? And mass is related to the number of particles that you have. I know. I deserve some bits for that. This has a small mass in the volume, okay? All right? A small mass in the volume, okay? All right? So the hot air one has a small mass in that volume because you have less particles, and particles have mass. In the large one, you have large mass in the volume because you have a large number of particles, okay? Okay, so the numbers that would come out from this would be giving you a low density, and this is the connection with the question. Okay, this is the connection with the question. So you see, this is the reason why you may have completely missed, and I've just basically had to teach you density. Okay, which is fine, because equals high density. There we go. Okay, so this is where the exciting bit is, and I'm going to try and race to get this mark as quickly as possible now. Okay, so you got large mass volume, high density. That would tend to now if you actually had a large mass, if the particles have a large mass, average mass, compared to the average mass of air particles, your density would be greater. So what would actually, the greater than air particles, so what would actually happen? If you've got like a comparatively huge density of these gas particles, so if you have a largely dense gas, a gas that's more dense than air, what's going to happen? Remember that small, light, low density gases rise. What's going to happen to large, heavy mass, heavy, dense gases? What are they going to do in air? If they're more dense than air, what are they going to do? Okay. So what do large density gases, which have larger densities than air, what are they going to do? What are they going to do? Okay. So knowing everything that I've just taken you through, what do large density gases? Larger density, they have larger masses. Yeah, larger, because if it's the same temperature as air, then you can assume that the distance between the particles are the same. So the only difference is the mass of the particles. So if they have larger masses, if the particles have larger masses than the particles of air, what will they do? Okay, will they sink? Will they stay in exactly the same level? Would they float in air? Like, would they float upwards? Would they sink downwards? Or would they just all like mix with air without any kind of change in density? What will they do? This is really interesting because this like, I didn't anticipate that you would have been so uncertain about density. It's very, very interesting. Come on, give me an answer. What will large density gases do? Will they sink? Will they float? Or will they just mix with air? They got large densities, so a large mass. They will fall. Correct. So, chlorine has been stated to you as being more dense than air. So you have now said that chlorine will fall, which is a big problem for the practical setup, because as soon as the gas forms, due to its large density, the gas will fall out of the gas jar. Okay. Even if you have a small amount forming right at the very beginning. So if you have like a small amount, yeah, then what will happen is that this will start. Oh, I want to move it. There it is. It will start to fall, and it will fall. So it's not going to be very good if you're trying to do an experiment that's collecting the gas, is it now? It won't be. Why will this not fall? Ah, there we go. Oh, stop it. But I think you get what I'm trying to say. Okay. Ah, maybe I need to, there it is. That's what I wanted to do. Okay. So what will happen is it will just fall, which isn't very good. Do you get why this setup is incorrect? Now, if you wanted to collect the gas, if it was like a small amount of gas, yeah, if you wanted to collect it, what would you need to do? So there's a small amount of gas that's formed. It's just falling. What will you need to do? What does this student need to correct? So how would you write that in? How would you write that down? Ooh, there's chlorine everywhere. How would you write that down? What does the student need to do? So the student should have now there is a way of answering this question even if you did not get the name of the gas jar. You can still answer the question without referring to the gas jar and still get them up. So what procedural change should the student do? And then we'll start talking about the other one. So to summarize, the chlorine gas is more dense than air, and the way that the apparatus is set up, the chlorine gas will fall out of the gas jar because the student has not done what? Here's another example of a gas that is more dense than air. I actually found the chemistry behind that and the physics behind it is quite interesting. The carbon dioxide is actually colorless, but it's actually at such a low temperature that the water vapor that's inside air, which is invisible, kind of coalesces. It actually turns into a liquid because it cools down rapidly, and those water droplets are what you see. You don't see the carbon dioxide, but you see the water droplets, and you have this fantastic smoke effect from what is actually a dry ice machine. So you can imagine that this is what is happening to the chlorine gas, because the chlorine gas is more dense than air as well. So what does the student need to do? What should they have done? Because the gas jar, the way the gas jar is positioned, all of the chlorine is coming out. So what do they need to do? Come on. What should they have done? No, not close Conical Flask 2. not close Conical Flask 2. Let me get a prompt. I'll be back. Don't worry, I've not walked out. Okay. Here is my gas jar. Okay. All right. Can you see that? Okay. Here is my representation of chlorine. Okay. Oh. Let's try again. Here is my representation of chlorine. Okay, now, my chlorine is denser than air. Okay? It doesn't seem to be staying in the gas jar. Yeah? Doesn't seem to be staying in the gas jar. Okay? Okay, so what can I do to the gas jar in order to contain the chlorine and keep it in there without any extra equipment? So what do I need to do? What do I need to do? I have a gas jar. I have chlorine. It's not staying in. What do I need to do? Without any extra pieces of equipment, what do I need to do? What does invert it mean? It's upside down. What's upside down? What? So what do I need to do? What do I need to do? What do I need to do? Quite enjoying this. Put upwards. What, put upwards? So I'm putting it upwards. There you go. I put it upwards. That's not helping. No, can't keep a hold of the chlorine that way. It's not worked. Make the whole face upwards. Make the whole face upwards. Do you mean turn it so that the opening faces upwards? Do you mean that? I think so. I think so. Now, congratulations. The hole is now facing upwards, the opening is now facing upwards, and I am now containing my chlorine. Why? Because chlorine's less dense than air. Now, if chlorine was more dense than air. If chlorine was less dense than air, I wouldn't need to worry about it, because the chlorine would float upwards like a hot air balloon. Yeah, and it would be contained in there. Now, you use the phrase invert, which sounds like a very, very unnatural phrase for a student to use. Yes. Okay. So, now invert was actually in the mark scheme. Okay. So, again, I hope either you chanced upon using a word that was in the mark scheme and you didn't know how or what it meant. Okay. Let's just hope it's that. Please don't. Just a general one. Don't use the mark scheme. All right. Don't use the mark scheme. So what the student should have done is positioned the gas jar opening upwards. Yeah, you know what it means. You know what it means. Okay, good. So the student should have put what the student should have. Wait. Let me just correct that. The student should have placed the gas jar opening. Place the gas jar opening the other way around. Okay, at the top. Okay, at the top. That's what they should have done. Right, and I'll fit it in as well. Okay, the student should have placed the gas jar opening the other way around. They should have put it. Should have put the opening at the top. Okay. Good. And what's the other? Now we can talk about the other mistake, right? Okay. So now we've got the chlorine. Where's the chlorine? Oh, hang on a second. I need to get the shapes. Okay. So what's actually happening? This is an easier one to understand. When you have the gas theoretically has to go through this delivery tube. Okay. It has to, in order to get into the gas jar. But the problem is that the gas can leak out. So what has the student made a mistake on? I think that's what you've already stated earlier. Now I'm just going to scroll up and scroll up and scroll up. Where is it? Okay, someone said, there's something that you use to close the second conical flask, but I don't know what it is called. Okay, you do need to close it. You need to use a bung. Okay? You need to use a bung. Okay? And a bung. Oh, okay. A rubber bung, yeah. Rubber bung. There we go. Okay? All right. So when you get a rubber bung, there we go. Like a 2-hole bung would be fine. Like one of these, okay? Like one of those. That will work. Yeah, 2-hole bung. So one to allow the chlorine to go into the concentrated sulfuric acid, and the other one to allow it to escape. Right. Okay. So once you've done your GCSEs, right, your summer vacation homework is to get yourself on a hot air balloon, okay, boys and girls, and start learning about density. Would that be okay? Right. The second one is there is no bung to keep the gas from escaping in the second flask. Okay, that's it. Right, the question goes on. Suggest one reason why the gas produced in flask 1 is passed through concentrated sulfuric acid. Now, concentrated sulfuric acid is a dehydrating agent. So it removes and dries the chlorine. Okay? Chlorine. Okay? Describe a test for chlorine. Wet litmus paper. I would use wet litmus paper because you need to dissolve the chlorine gas into water, okay, to activate the test. The observation. Now, when you use blue litmus paper, okay, so e.g. blue, when you use blue, it initially goes red, okay, and then it bleaches. After an initial change to red, the litmus paper bleaches to white. Okay, that's basically the answer that I would put. In the exam, they may actually just insist on bleaches to white, and that would be good enough to get the mark. But I've done this test so many times that I can't decline that it actually does go red first, because you make chloric acid first, not chloric acid first, I believe. Okay. So it's more than harmful. It'll kill you. It's more than harmful. It's not going to just like, oh, look, there's a bit of a rash. It's more than harmful. They used it in the Second World War. It will kill you. Yeah? So it's toxic. Toxic. You need to expand your repertoire of words. There's a difference between corrosive, harmful, toxic, radioactive, explosive. Yeah? All right? So, harmful is a big yikes, yeah. Harmful, all right. It will kill you. Now that's that chlorine. You need to know. You need to know chlorine is harmful, more than harmful. Yeah. All right. Question number two. So, okay, right. So this is the question that has a lot of words in. Okay. So basically, let me take you through this one. There's a reaction between sodium carbonate and barium nitrate. You actually make a precipitate, okay? The precipitate is barium carbonate, all right? That's precipitate. Now, if you have your wits about you in your exam, you'd actually and remember that this is for like paper 4 and paper 2 students also have to do this. So you get like a yes, it would. No, you can't check the mark scheme for that. It's just the wrong answer. Yeah, harmful it will not be good enough to get the mark. Precipitate is barium carbonate. The best candidates will actually spot that because they will have learned the solubilities of the different solids, like sodium salts are very, very soluble, for example. Okay, but barium carbonate is definitely 100%, right? And that's it. So, but it won't stop you from doing this question. Okay. But the best candidates will actually look at that and they'll think, oh yeah, this is about precipitation of barium carbonate. Now, you may not necessarily have met this experiment before. Again, this is like an alternative to practical. So again, that should not stop you from accessing this question either. Okay. All right. So what I'm trying to say is that this question is doable. Okay, this question is doable. So a burette, filled with aqueous sodium. So burette, right? Just to measure precise volumes. Okay, that's all it is. Okay, that's all it is. You could use a syringe, like a liquid syringe. You could use a squeezy pipette. They've used a burette just for accuracy. Okay, that's fine. 7 test tubes labeled 1, 2, 3, 4, 5, 6, 7. Okay, now there's something very important for you to look at on this one. And if you don't notice this, this is why you have to go through this, right? It is a heartache. You do have to read through this, but you have to read through it. And what you need to do is you need to note that there is it doesn't go from 2 to 3. It goes from 2 to 4. Okay, so 3 is missing. All right. So 1 is added to 1. 2 is added to 2. Now 4 is added to 3. Okay, that's going to have an effect on the graph that we have to do. 5 is added to 4, 6 is added to 5, 7 is added to 6, 8. So basically what you're doing is you're adding more and more sodium carbonate to barium nitrate, and you're getting more and more precipitate forming until maybe your sodium carbonate, your barium nitrate is in excess. And your sodium carbonate can no longer precipitate because you need the carbonate ion in order to make this precipitate. Okay, right. The rest of it is procedural. Glass rod used to stir the contents of each of the test tubes. Contents of test tubes were left to stand until the solid formed. A ruler, so until the solid formed and settled means that it's settling at the bottom. Now that's very, very important. Okay, that's a very important word. It settles at the bottom. Okay, so your precipitate, which is an insoluble solid, you should know by now, precipitate solid settles. That's very, very important. That's why that's the second most important phrase here. Okay, so the first point is 4, not 3. The second one is that it settles. And if you don't get the settles bit, you're going to absolutely botch the next question. Okay? So a ruler was used. Now it says use a ruler to measure the height of the solid. So because of the limitations of... I'm going to see if this works. Okay, let's have a look. Let's have a look. Here we go. Right. Now, the good news is that they also remind you at the bottom, just in case. But when you're actually reading that, like when you read a fact, you kind of think, no, maybe not. That solid thing right at the very bottom, it reinforces it, and when you're actually doing this in an exam, it actually then sticks in your mind. You've been told this twice. Okay, right. So the measurements that you have to take are this. Okay. All right. This. Now remember, on the day, you'd use your ruler, yeah? And because this is on, there is a limitation to streaming because if I zoom in, it's going to be a different distance. Okay, so what I'm going to do is I'm just going to basically, I don't like that, right at the bottom here. Okay, now you'll notice, remember what I said earlier? That you'll get the amount of precipitate increasing, which is what you get from 1 to 5, until you get to a stage where the barium nitrate is in excess because all of the sodium carbonate has reacted. There's no more carbonate to react with the increase in barium nitrate that you're adding. Okay. So when you do that on the day, and if you print this out as well, if you print this paper out and you're actually doing it, you may not even get the correct heights, because your print might actually be at a different scale. Your printer may have different margins, okay? But the numbers that were needed on the day were 12, 24, 48, 60, 73, 73, because it stays the same. There's an excess of barium nitrate here. Okay, so those are the numbers. All right. Now, don't forget that you've also got to do the volumes. Okay, you've also got to do the volumes. So the volumes. Now notice that the volumes are they're not labeled. It's only the solids that are labeled, right? It's only the solids that are labeled, all right? So you may start to think, right, okay, I need to measure this. How on earth can I measure this? Yeah, you might be like that, okay? But read the question again, right? Test tube number 1, the volume of aqueous sodium carbonate. Let me get my box. That's the volume, okay? Let's just re-emphasize that. There we go. All right. So the volume, that goes there. Okay. That goes there. Okay. That goes there. All right. Yeah, it will be full. Don't worry about that. Yeah, number 4 goes there. Okay. I'll just go through this. Number 5. That one goes there. Number 6. So that extra reading will actually earn you marks. There we go. And then the final one, there we go. That goes there. Okay. Okay. So you should get 1, 2, 4, 5, 6, 7, and 8. Okay. You should get 1, 2, 4, 5, 6, 7, and 8. I'll just put those in. All right. Is everyone okay with that? Now you're gonna get a question like that somewhere in your paper 6. So always, every single year, you'll have something like that. So yeah, you're gonna have to dig deep for that one. You're gonna have to do some reading. Yeah. All right. And that's probably an easier question than like the gas jar question. But the gas jar question, no, I'm not even going to talk about hot air balloons again. Right? Don't get me started on that. Now that's a solid 3 marks. Okay, so. There's no extra knowledge. All right, okay, you would have been quite savvy about it if you actually knew that the precipitate was barium carbonate. But there's no extra information that you require for that. So you have to make sure that you get those. Right, okay. Now, plot the results on the grid. Right, okay, this is where it gets really interesting. Right, so you got 1, 2, 4, 5, 6, 7, 8. Right, I'm gonna just copy that. Can I copy? Yeah. No. Let's have a look. Now, this would have been across a double page spread. Okay. I don't know what's happened here, but okay. Right. So what I would suggest that you do, let me see if I can get a display with both pages at the same time. 2 pages, there we go. Right, that helps. Okay. Can you still see that? Yeah? Okay. All right, so what I would do when I'm doing this, because remember, this is a walkthrough, okay? So what I would do is I would, now it says draw two intersecting lines of best fit, label the x-axis, right? So the height of the solid is that one there, okay? That's the height of the solid, all right? So what I would do first and foremost is I would actually put the axis, all right? And what you have to do is you have to do volume of aqueous sodium carbonate, and you have to put the unit there as well. I'm about to put 3. Okay, and I'll put that there. Okay, there we go. All right, so you get your 1 mark for that. Okay, then what I would do is this: I would actually just knock off where you actually need to put the plots. So I'll do this in pencil. 1, 2, 4, 5, 6, 7, and 8. So you actually have a visual check. Okay, you actually have a visual check, a visual guide. And now what it is the 12, right? So you have, so these over here, right? So each one of these jumps is worth 2. You know that because if you go like 20 blocks is 10 small squares. Okay, 20 blocks is 10 small squares. Now I have to explain this because I saw too many errors in the mock exam. Okay, so each block is 20 divided by 10 equals 2. Okay, block, I should say block. There we go. So so the first one that you do, let's have a look. Let me just do text box here, 24. I'll just do it up here, right? It's just easier for me to display it. Okay, I'll just go to 1 because now I need to show you exactly where it is. All right. Okay, so the first one is 112. Okay. Oh, what happened here? 1, 12, 24, 48, 60. So let me just move this. Hold on a second. Okay, for the screen. Sorry, guys. There we go. There we go. All right. Okay. So, so the first one is 1 goes to 12, right? Okay. So let's have a look. Now, what I want to do, I want to see if amazing. Right. Okay. Excellent. Right. Okay. So. And what I want is, I want that to be a slightly bigger font, so bear with me. Where's the X? There it is. Brilliant. Okay, right. So let me just turn that ink to red. There we go. Okay, right, so can I duplicate that as well? You know what I could just do? I could just do it in like a text X, so it doesn't matter. Oh, that's horrible font. That's horrible. Do plus. Yeah, I'll just do it as pluses then. That's fine. Sorry, guys. This worked in This worked in rehearsals, and it's because I changed the font. Right, okay, so let's have a look. So let's get that one here. So that goes on 1, 2, 4, 6, 8, 10, 12. Okay, all right, has to go there. Then the next one. Can you see these, by the way, or do I need to make it a little bit bigger? 22, 24, and make sure you use a ruler. Okay. Now, remember to skip 3. Okay, you've got to skip 3. Okay, now this has to go to 48. I'm telling you, one of you are going to make this error. Okay, and you're going to mess up like royally. 42, 44, 46, 48. Okay, you're going to mess up. You're going to not skip 3. Make sure it's not you. Okay. Okay. Oh, now the X's are working. Fine. 60. That's a nice one. Now at this stage, when you do your graph, at this stage, my big, no problem, Chill Beans. My big tip for you is this, gives Chill Beans a chance to restart as well. When you have something like 3 or 2 points left, don't start getting what we call cocky about it. All right, don't say, oh yeah. The number of times I was marking the mock exam, right, and I found errors in the last 2 or 3. This, I'm telling you, do not get overconfident. At this stage, I would actually take a breather back, and I would say, am I doing the right thing? Check it carefully, and then go back. All right. All right, don't get overconfident about it. All right, the next point is the 6, and this would be at 73. Now 73 has to be halfway through. All right, so they're testing you on that one. At 70, 72 has to be halfway between 72 and 74. Okay, and and that has to be in line as well. I wasn't happy about that. It was a little bit budge. Now, when you're an examiner, you have to check every single point. Yeah, I didn't even like that one. And I'm telling you, don't think that they're just going to look at it and think, yeah, I'll allow it. It looks great. They're going to check every single point. And not only that, from the examiner's point of view, I can tell you that because I'm an examiner, right? If you are more than half a square out, I tell you one thing, they're going to be ruthless. Half a square out where it should be. If it's more than half a square out, you won't get it. It's as simple as that. So all that 5 minutes or whatever it is that you took to do this, and here's the additional thing as well. All right, you got to do this quick. All right, don't let this be like a 7-8 minutes where you're in the middle of an exam, right? And like you're thinking, oh, life is great, life is beautiful. You know, I'm going to be a doctor, and all I need to do is just put a plus or a cross on the graph. Okay? All right? Because I tell you one thing, this can become like a 10-minute coloring in exercise. You got to be quick about this. So all of these things need to be done quick. Now, plot the results. Draw 2 intersecting lines of best fit. Okay? 2 intersecting lines of best fit, right? And then label the axis. Okay? So how much of that have we done already? 2 intersecting straight line graphs drawn with a ruler. Now, let's see where our lines are. Now, it does make sense. It does make sense. They're not going to get you on this one, but it does make sense that this is too thick. It does make sense that when you have 0 sodium carbonate, you should have no solid. So 0, 0 is actually a valid point, but it's not something that they're going to, you know. Now, there's the first line. Okay, 2 intersecting lines. There's the first line. And there's the second line. Okay, now you're going to have to do this with a ruler. Okay. 2 intersecting lines are best fit. There we go. All right, that's the best one. That's better actually. I'm going to redo those again because you would have done this in pencil, right? Now I'm going to double check because not all the lines actually always go through 0, 0, but that's fine. I'd do that. I'd go with that. Remember, with lines of best fit, you have to have the same number on either side of the line. So I would say that those two are marginally on the left-hand side and these two are marginally on the right-hand side. These are all in the straight line, so that should be a straight line all the way across to 73. There we go. All right. That's your 2 intersecting lines straight, drawn with the ruler. All 7 plotted correctly. That's 2 marks. 2 marks, okay? You don't plot one of those points, you're going to drop 2 marks immediately, okay? And then the last axis is, the last mark is for the axis, okay? All right, is everyone okay with that? From your, welcome back as well. From your graph, deduce the height of the solid form when 3, right? Now, you actually, if you fluff your lines and you have an absolute meltdown with your graph, do this question still. Because what they will have to do is they will check your graph, okay? They will check your graph. And they'll verify it. Okay, and you can still pick up this mark even if you did not plot correctly. That's 38, okay? Millimeters. Okay. And where it says show, you show. You show. Okay, you show until there is no more show, okay? Now, let me just double check to make sure that I'm doing okay. When 3 is added to 6, yeah. 3 is added to 6 and each one was 6. Okay, all right, each one was 6, so you're absolutely fine. That was my little check, okay? So the answer is 38. Okay. Okay. 38. All right. All right. So what they're going to do is they're going to assess that with a value from the graph, okay? And that's what they mean. All right. This is why mark schemes really, really do not do any help whatsoever with students' graph skills. Okay. So this is why the walkthrough is really, really important. Okay. Got 11 minutes left for today. Describe the trend in the heights. All right. And this is what I teach my year 8s. Okay, this is what I teach my year 8s. As the And then what you have to do is you have to say like increases, decreases, increase exponentially, right? Describe the trend in the heights of the solids formed in test tube 1 to 7. Okay, now test tube 1 to 7 talks about all of them until test tube test tube 6. Okay, then the height does not change when you add barium nitrate, when you increase the volume of, what is it, sodium carbonate? It should be sodium, wait a minute a second. What was added? What was added? Until you, sodium carbonate should be sodium carbonate. Sorry, sodium carbonate. Okay. And then you can just say test tube. Test tubes 5 to 7. Okay, so this one is as the, so for this is why I teach my year 7s, right? You basically copy and paste the phrases in. Okay, you copy and paste the axes in. All right, as the volume of aqueous increases, okay, added, and then you get this trend because this, as this is going up, wait, ooh, come on, I want to rotate this. How can I rotate this? Oh, that's not doing what I wanted to do. Right, let me try again. I should do it with lines. So as this increases, as that increases, and you can see that on the axis, this increases, and you can see that on the axis, until, and it only works in this zone. It only works in this zone. Okay. And test tube 5 is where you added 6. Okay. All right. Increases. So the height of the solid. Oops. Delete the right bit. 5 to 7. Okay. There we go. So you could put remains constant. Now that nails it. Okay, that nails the mark, the 2 marks. And you're gonna have to say it in a way that is not fluffy. Don't be fluffy. Okay, so you have to say it in a way that's not fluffy. Make the point and make the points well. Okay, make the points well. Is that quite clear, everyone? Yeah. Because you could be fluffy right now, you could be fluffy in class, you could be fluffy to your friends, okay? But when it comes to the exam, I want you to be William Shakespeare, right? You got to be absolutely sharp with your descriptions. I hope that's very clear, boys and girls. Predict what would happen if the experiment was continued using 3 further test tubes, each containing 6, but you're separately adding 9, 10, and 11. So what you're not going to have is you're not going to have any increase in the height. Okay. So the height of the solid does not change and remains at 73 millimeters as all of the barium nitrate has reacted and the sodium carbonate is now in excess. Okay, simple. All right, that's a nice 2 marks to get. Okay, I like that. Nice 2 marks to get. Let's just make it a little bit bigger for you to see. There we go. Just one change to the apparatus used may obtain more accurate results. Okay, so when you go back to the experiment, you'll notice that where is it? A measuring cylinder was used, and that's